Okay, are there any questions before we get started today? So I'm still trying to work out a little bit if there's a way that we can do the split class. It seems like most people are right with it. There are a few objectives, and I want to make sure that it worked for everybody. Do we get solutions or answers to assignment 1? I will grade. I'll grade them out and return them to you with notes. That'll probably happen. My goal is to have that done by Friday. It's going to depend a little bit on another project that I'm working on right now, but it should. But I would like the turnaround time for the assignments to be less than a week. So, yeah. Any other questions? Okay, so today we're going to have a two-part lecture. And the first part is going to be a sort of standard lecture like we've been doing. And then in the second part, we're going to be starting with a little bit of the programming. So in particular, solving differential equations using Python. And so if you have Python and Jupyter installed, I've created a module on the Canvas site. So the module is for week 2. And you can download the Jupyter Notebook file from there. And if you don't, then we'll be able to access it through Google. So hopefully that will cover everybody, but we will take a few minutes to make sure that everyone's actually logged in and able to access the material. Okay. Great. Any other questions before we get started? All right. So what we want to talk about today is basically autonomous differential equations. And at least a first view at population models. Okay, so let's recall quickly just from problem set 3. We had this this idea of a slope plot, right? And I showed you one example last Wednesday, and then we then you did an example or two in problem set 3. But the idea, straightforward. The idea is that basically for a first order differential equation, like as an example, dy dt equals t minus 3y. What this is telling us is some very, very direct information about the derivative, right? So we can directly use the equation to draw a sort of chart of the slopes. Plot of slopes of the solutions. And so in this case, for instance, if we have this differential equation, we have y and we have t. We could, for instance, mark off a grid, right? So 1, 2, 3, 4, 1, 2, 3, 4. And for all the values, so make ourselves a little table. And for y and t equals 1, 2, 3, 4, 1, 2, 3, 4, we could find the slope. So here this is dy dt. Okay, so for t equals 1 and y equals 1, we're going to have minus 2. For t equals 2 and y equals 1, we're going to have minus 1. For t equals 3 and y equals 1, we're going to have 0, 1, etc. For t equals 1 and y equals 2, we're going to have what? Minus 5, minus 4, minus 3, minus 2, minus 8, minus 7, minus 6, minus 5, minus 11, minus 10, minus 9, minus 8. And these are then going to be the slope of the solution at each of these points. And so, for instance, we could kind of chart this, right? So at minus 2, we can say, well, what's going to be happening? So then at 1, 1, oops. At 1, 1, the slope is negative, and so the solution will be decreasing, right? At 1, 2, well, the slope is still negative, but not quite as negative. So the solution will be decreasing, but not as sharply. And at 3, 1, it will have flattened out. And at 4, 1, it will be increasing. And similarly, at 1, 2, it'll be very, very steep, and then even steeper and even steeper. At 3. And so we get a kind of picture a little bit of what is going on with these solutions. And we could, of course, extend this both down to the axis and below. If we extend it down to the axis, at 0, 0, we get something like this. At 0, 1, we get something positive. 0, 2, very positive, even more positive, even more positive. Minus 1, etc. Okay. So are there any questions quickly? I know you guys did this on your homework. I just wanted to go through and kind of do a careful example. Okay, so one thing that this allows us to do two things. Oh, what is the purpose of this graph? Good question. So this allows us to do two things. So one, we can estimate solutions, right? So we can use this plot to estimate solutions. So for instance, how do we do that? Well, we say if we start here, we can sort of either in a sort of hand waving way, kind of say, well, okay, so right, so what we can sort of look at the shape. We know that the solution has to be tangent to the line at each point. And we can kind of estimate the solutions by trying to draw lines of tangency. We can actually do something that's a lot more precise as well. This doesn't have an undo when you're in this mode, is a little annoying, but so if we want to be a little bit more exact, what you can actually do to estimate solutions by drawing a curve tangent to each slope line. And the other way is we can draw piecewise linear curves. Linear, right? So starting here, we say, well, we'll start here, and then we'll just follow this line to here. Great, then we'll follow this down to about, where we would hit the next grid point, increase, increase, etc. In this way of following things piecewise in a piecewise linear fashion, right, where what do? We go to our initial point, we compute the slope, we draw a line through that point with that slope, we go out a little bit, and then we compute it again, and compute it again, and compute it again, and compute it again. This is the most, in the most simple sense, this is how numerical solvers work. So this is how solvers, well, I'll say maybe used to work. No, they still work this way. This is how numerical solvers work in the simplest sense. Modern numerical solvers are a lot more sophisticated. So they'll kind of start off doing something like this, then they've got all kinds of approximations and whatnot they can do, and even looking at things like the form of the differential equation and trying to anticipate what the best way to solve it's going to be. In particular, they also try to do things like handle exploding derivatives, which we'll see some examples of in the second part of the lecture. But so this is the first thing that you do. Basically, you look at this plot and you try to get some specific information about the solutions, right? Now, of course, this is like a sketch. This plot is not, I did not sit down here and like rigorously measure the angles. In a very large sense, I'm just trying to get kind of a general picture of what's going on. And that's really the second thing, so that we can get a general picture of specific solutions, or we can estimate specific solutions. And of course, if we do it numerically, we can estimate them much more precisely. But the second thing is we want to get a picture of the possible behavior for the different types of solutions. I should actually, I'll say even, we want to get a global picture. And this is really important. There can be a tendency to basically, you see a differential equation and you want to solve it and just get an answer. But it's much more helpful, and we'll start to see examples of this even today, to be able to look at a differential equation and say, well, what is the possible solution space, and how do these solutions actually behave, right? Is there any possibility that that this differential equation could model the kind of behavior that I'm interested in? And another big thing is, does this differential equation, so in the modeling that it's doing, what kinds of solutions can we expect, right? In this equation that we've written down here, you're starting to kind of see, but it almost looks like all of the solutions kind of are eventually going to wind up following some sort of asymptotic line, right? Or some asymptotic curve. And, exercise, solve the equation and show that that's in fact the case. They do sort of all converge into the same curve. But that may not be the case, right? It could be that there's two such solutions or many such solutions, or the behavior is completely chaotic. And knowing that about the solution space is very important, because at the end of the day, when we go out into the real world and we fix our parameters, right, there will always be errors, right? There's always going to be error bars. And if you have very, very, very sensitive equations, right, where, for instance, a slight change in one of the parameters could completely flip the solution style from being something like asymptotically stable to asymptotically unstable, that might not be a great candidate for a differential equation, or for a model of your system, if especially you never see the instability come out, right? Or the other side of things. So, and this is, you should not bank on this. But so in general, your takeaway is that if it's very, very easy to go between stable and unstable solutions, you should be a little bit suspicious. You should be very, very careful about especially if you don't observe that kind of behavior. But there have also been cases, and there's a big one going on in sort of the quantum physics world right now, of these exact kind of instabilities happening, where it just should not be the case that that everything cancels out so that all of these unstable factors actually become stable, but they do. And that then, if you wind up in a situation like that, where the model works really, really well, and it looks like it should be unstable, but through some conspiracy of coefficients, it's not, then that might imply that there's some sort of deeper, simpler theory being buried beneath the complexity, or some strong reason why the coefficients are the way that they are. And so this little local picture for estimating solutions is important, but really actually what we want out of slope plots is we want to get a view of the global picture. Any questions? Throughout this class, we'll see quite a few different representations of differential equations that are going to try to allow us to do this. To look at the equation not as a single solution, but as an entire family of solutions, and really understand that whole family. Let me do another quick example. So again, what are we looking for in slope plots? And the big thing to look for is different families of behavior. And especially asymptotic behavior here. So quick example, if we have very hard to draw straight lines on the smooth kind of tablet thing. Okay, so let's say that we have our domain, our range, and we want to look at dy dt equals something like 3 minus y. So with a little bit of work, you could go off and solve it. So the solution is just going to be, so the implication here is that y is equal to 3 minus y naught e minus t. And I'll just draw a little cartoon of the slope plot. Four. And if we wanted to go through and do some calculation and build the grid like we did before, and I'm more than happy to do that if you want to see it. But what we'll find is that when y equals 0, the slope is 3. And interestingly, it's 3 everywhere, right? When y equals 1, the slope is 2. And it doesn't matter what t is, it'll always be 2. And when y equals 2, the slope is 1. And then when it's 3, the slope is 0. And when it's 4, it's minus 1. And similarly, when it's 5, it would be minus 2. Okay, so what do you notice globally about this slope plot? What does the slope plot tell you about the possible space of solutions? So the solution has a horizontal asymptote, yeah. But in particular, every solution has a horizontal asymptote, right? So there doesn't. So in fact, in a certain sense anyway, there is maybe only one family of solutions, right? In the asymptotic sense. So it's absolutely correct, right? All of the solutions have a horizontal asymptote and at the same value, right? You could imagine a situation in which all of the solutions had a horizontal asymptote, but maybe it wasn't at the same value. We'll look at some of those in a second. So in particular, so we see that all solutions are asymptotic. To 3. And so that tells us a lot about the model, right? We could, of course, figure that out by staring at the form of this equation here, right? If we look at this equation, what we find is that, of course, for any initial y naught value, this e to the minus t is eventually going to kill it off, right? When t is large, this is going to go to 0, and we're just going to get y equals 3. Okay, great. But there's kind of two things about this. So one, sometimes it can be kind of hard to see that by staring at the equations, and it can be much easier to see it by looking at the slope plot. And there's always, in mathematics, like mathematics is hard enough. You should always do what you can to make your life easier. And so if you can see what the behavior must be by looking at the slope plot, you can then go and prove it carefully from the formulas. The second thing, of course, is that, and we'll see some examples. I mean, at the end of this, well, at the end of this lecture in a couple minutes, it's entirely possible to write down completely rational-looking differential equations that we can't really solve, right? And the examples that we'll see here are going to be examples where, well, we can sort of do the integration even. The issue is that the formulas aren't, we sort of can't solve the formulas that we get afterwards, right? We can successfully do the integration, and so then we get, okay, some, function of y equals some function of x. But we can't get an explicit solution. And we'll be able to sort of manipulate those formulas and find out information about the asymptotics, but we can actually generate a very nice picture just by looking at these slope plots. And we can get a huge amount of global information by looking at them about the solutions. And so, of course, with slope plots, this will only work for first order differential equations. Right? There's other pictures you can draw in the higher order cases, but this is heavily dependent on the fact that that we're only dealing with the first derivative. Right? We have an explicit equation for the first derivative in terms of the values of the dependent variable in the function. Okay. Any questions? Okay, so there's another interesting thing about this that I want to point out. We'll talk about it more in a second, but basically, see the solutions are asymptotic to 3. Well, I should say are asymptotic to the constant solution. Y of t equals 3. So we call such a constant solution an equilibrium solution. We'll have more to say about that in a few minutes. But there's another thing to notice about this equation, and we'll make this a little bit precise in a second. But if you notice, the derivative, the slope dy dt, doesn't actually depend on t. So in this case, dy dt doesn't depend on t. Right? If you notice when I was talking about the solutions before, so it doesn't matter what the value of t is. If y is equal to 1, then dy dt is 3 minus 1 is 2, no matter what the value of t is. So this is in contrast, if you notice, so basically, if we go horizontally, the slopes don't change. This is in contrast to this picture up here, right? Whereas we go horizontally, the slopes actually change quite a bit. And it really restricts the behavior, the possible behaviors we can get out of such a differential equation. And there's a name for this. We call such equations autonomous. Autonomous differential equations have some very nice properties. They are also a lot more common than you would think. And the reason is that if you think about it, if we have to crowbar time into the differential equation explicitly, then inherently we're thinking about a situation in which the interactions, the fundamental rules that we're positing change over time, right? And there's a lot of situations in which that's true, right? Where, what happens on Tuesday is not the same as what happens on Friday. But there's a lot of situations, especially if you're trying to sort of model fundamental interactions, where you don't want that to be true, right? Think again about, the big sort of most important example of mathematical modeling, physics, right? Where, the kinds of interactions that you're really trying to model there, you want to be able to say something like very fundamental, right? That in fact, like, this is how these interactions work for all time, no matter what, right? You don't really want time to appear in your interaction equations. And with a lot of things like population growth and epidemiological models and these kinds of models that we're going to discuss in this class, we sort of want the same thing to be the case, right? We want to posit some fundamental interactions between people or animals or E. coli or systems within our body or whatever they are. And then we want everything else to follow from those fundamental interactions. As soon as we have to actually add in things changing over time, we lose a little bit of the power of the sort of armchair view of differential equations, where we can sit there and think about how these interactions must work and then spin out these complicated results. Now, that said, of course, in a lot of modeling, things do change with time and situations change with time. Or another thing that will often happen is parameters will change with time. And in that case, then we absolutely should expect to have a non-autonomous differential equation. But this autonomous condition seems very strong. And in fact, though, autonomous differential equations do show up a lot. Okay. So are there any questions? Okay. So take a look quickly at population growth. All right, so there's a couple of different ways to motivate the following model. And I personally like to think about these models in terms of probabilities, in a very rough sense. But the idea basically is the following. So for a population P, over some time scale, let's posit some. We want to understand basically how the population is going to grow, or is going to increase or decrease, right? So for population P, on some time scale, let's say that each member has an alpha % chance of giving birth and a beta % chance of dying. Or let's just start with each member has an alpha % chance of giving birth. So leave dying out of it for the moment. So as a quick example, if we have 10 amoeba, and bacteria, each of which has a 50% chance of reproducing each, I don't know, day, say. Each has a 50% chance of reproducing each day. Then we would expect at P of t plus 1 days, we would have P of t bacteria plus, well, if each one has a 50% chance, then 0.5 times P of t, roughly. Now, of course, this is an expectation value. If we actually wanted to be careful and put in our probability hats, then we would have to be a little bit more careful about, about exactly what we were saying here. But if we want to, if you don't like 10 bacteria, then let's call it 10 million bacteria, and then this, then the probability should basically wash out. Okay. So after half a day, how much would we expect? Well, after half a day, we're going to expect the same number of bacteria we had before, plus half of the amount that we would expect after a day. And similarly, I mean, we can already see if we had a fourth of a day or a tenth of a day or whatever it is, or 2 days. So after 2 days, we would expect the population to double. And in general, after delta t time has passed, what does that mean? It means that we expect P of t plus delta t is P of t plus delta t times 0.5 times P of t. Or subtracting and dividing, right? We get that P of t plus delta t minus P of t divided by delta t is 0.5 times P of t, taking the limit we're going to find that dp dt, actually say which limit I'm taking, equals p. Okay. So the idea here is if there's a certain probability, alpha, that any member of the population reproduces, as an example, that any member of the population doubles, that for each member of the population, there's a probability alpha that a new member comes in over some time frame, then the differential equation that we write down is actually dp dt equals alpha times p. Or in general, dp dt is alpha p. Okay, and we all know the solution to this differential equation. The solution is just going to be e to the alpha p, or c times e to the alpha p. And in particular, this has unconstrained growth, right? If alpha is positive, and if alpha is negative, it has unconstrained decay. Okay, are there any questions though? So we're going to complicate this model here in just a second. But this reasoning of basically, if you have a certain probability of reproducing, then the differential equation that you write down is linear, it's kind of it's important to convince yourself of. And there's different pictures of it. But I do want to pause and ask if there are any questions. It's not necessarily as straightforward as you'd think. It is certainly not the only thing that you could write down. Okay, well, let's complicate this a little bit then. So density dependent growth. So this is the most straightforward thing. Birth, death. Let's complicate this slightly. So now let's say that every member of the population, so say every member of the population has an alpha chance of reproducing on average, and a beta % chance of dying. Each time period. We could draw a compartment model, and the compartment model here, of course, is going to be got some rate in, we've got some rate out, we've got P of t, we've got a birth rate alpha, and a death rate. Beta. These are both probabilities, so when we write the equation down, they're both going to be linear probabilities, and we're going to get, so they're both going to be linear terms in the equation. We're going to get alpha times p minus beta times p, or r times p, where r is just alpha minus beta. Setting r to alpha minus beta, we get dp dt equals rp. Okay, and now there's two phases for this, right? Two phases for the equation. So a phase roughly is a set of behaviors for solutions based on certain parameters. So in this case, the first phase is going to be uncontrolled growth. Right here, the solutions are, so it's going to be P equals P naught e to the RT. And what is the other phase? So if one phase here is uncontrolled growth, what is the other phase going to be? Trending to zero, exactly. Uncontrolled, asymptotic decay. actually, yeah. So, growth and die off. And quickly, what separates these two conditions? What determines whether or not we're going to see uncontrolled growth or whether we're going to see die off? The sign of, yeah, gamma is actually probably a better variable to use for it. I was using R, but so when R is greater than 0, and here when R is less than 0, and the function is p naught e to the RT. Great. And so we could have drawn these as the slope plot. In this case, we all know what the solution to this differential equation looks like, so I just drew it out. But we see that for a fixed value of R, we could get a lot of information about all possible solutions. And now we actually even want to go a step farther, right? We want to think about this as a model sort of within parameter space as well. And we want to think about how the families of solutions change depending on the model. And this is a case, right, where I said, again, we need to, so we have a phase change here. So if we were to go out and study a system and we saw that, in fact, ecological systems never experienced this kind of die-off, right? That would make us a little bit suspicious. But in fact, what we see when we look at ecological systems is this kind of die-off actually happens quite often, right? Where you can have nice sort of exponential growth, and then all of a sudden something flips. The food supply doesn't quite match what it needs, and all of a sudden the population declines and declines fast. Of course, the situation's a little bit more complicated than that, but for a simple model, this is basically the full analysis of the simple model, right? We have two phases, uncontrolled growth, uncontrolled die-off, and they depend entirely on the difference between the birth rate and the death rate. Basically, if the birth rate's larger than the death rate, then we're going to have uncontrolled growth. If the birth rate is not as large as the death rate, then we're going to have uncontrolled die-off. Okay. Any questions? All right. So let's then complicate this even a little bit farther and talk about density-dependent growth. So I'm gonna spin out two pictures here. The idea is to include competition. Include competition / crowding within the species. Or within the population. We'll talk later about how to include competition between populations. We need to build up some machinery before we can do that. So basically, one picture. So assume resources are scarce. And assume that basically that there's there is a gamma % chance that any two members of the population will come in contact. will come in contact and therefore compete. Okay, so then what do we have? So what that will mean is that, and compete, and I should say, and compete in a way that one of the members of the population will die. In a way. Kills one member of the population. All right. So what that means is that we have the following. So then we have that dp dt is going to say, okay, we'll still have some birth rate, right? And we'll still have some natural death rate. But we also have a death rate that is based on the probability that you meet somebody, right, times the number of people in the population. So this is a death rate. And so that means that for each member of the population, they also have a death rate based on the probability of coming into competition with somebody else times the number of other species. So just like here, this is a rate. This is a rate, right? In this case, the rate of death is the rate of death itself is proportional to the number of members of the population, right? In particular, if the population doubles, we would expect the possibility of competition to double, and so the death rate due to competition to double. Again, it's a relatively simple model, but we can rewrite this then as R times P times 1 minus gamma over, RP. Where here R again is going to be alpha minus beta. Okay, are there any questions about this? Do you believe me? Does this make sense as a simple model of population competition? There is another explanation I can give if there's interest, or maybe more. Yeah. Yeah. So let me give a second explanation of. So I'll repeat the death rate part and then let me know if it makes sense. And if not, there's a second explanation that I can give in terms of sort of discretizing. But basically, let's assume that we have that there's a certain percentage chance that any two elements of the species will meet competitively, right? So this could mean fighting over food. This could mean fighting amongst themselves. This could mean any kind of competitive competition that will then result in the members of the population not being able to reproduce, right? Or sorry, not being able to reproduce, that will actually result in them dying. That means that, so if let's say that for every member of the population, there's a 10% chance that it will meet another member of the population. So we think then what that means is that for one guy, death rate through heredity is also included in that. Yeah, so the death rate through heredity is just this beta over here. This is our old death rate. second old death rate, and this here is the birth rate. So, okay, so then what is a rate again? Well, a rate is just a certain probability that one member of the species will die, right? So the probability that one member of the species will die now depends on how many members of the species there are, right? Because, well, there's some probability of one member of the species encountering one other member of the species. And then that will then increase linearly with the number of species present, right? So in particular, if you have a 10% probability of meeting any one person, right? Just based on, just sort of based on the habits of the space that you're in, right? And suddenly the population doubles. You should then have a 20% chance of meeting any one person. And so the way that we break this up is by saying that there's a simple rate of competition, and then that rate of and then the death rate. So the overall death rate from that rate of competition is given by the rate of competition times the current population, and then each member of the population experiences that death rate. So the total rate of change is the death rate times the population, where the death rate depends on the amount of population present. Let me give another example. I'm not sure if that's clear, but maybe are there any questions before I do give the other example? Or another explanation. So the other explanation, say an alternative explanation, is, so assume that we have, assume for instance that there's like n sites that have food. Assume there's n sites and m of them have food. So the picture is that we have some grid where we all live, as little E. coli or something like that. So these are food. These are sites. So for each member of the population, basically, if you want to survive to the next stage, you have to get food. So to survive, each population member must get one food. Yes, so there's there's definitely an analogy with the gamma term there, right? That it's and that this is exactly the gamma term that we'll use in the SIR model. So the size question, just in case people are on chat, is suppose a person gets admitted to a hospital and meets another infected person and both of them die. In this case, so is this case included in gamma term, right? So we would expect that this is going to be an interaction between two different populations, an infected population and a non-infected population. But we would expect the number, if we double the non-infected population, then the number of interactions should double. Just like if we double the number of infected populations, the number of interactions should double. So there should be some base rate of transference, gamma, and that will be a coefficient of infected times uninfected. So in this case, yeah, it's a good observation. So in this case, so to survive, each population member must get food. So then what is the percent chance of survival? Well, to first order, it's going to be, so, well, you've got an M and N chance. So you have each member has an M and N chance of landing on food, just picking randomly. Right, so in this situation, sorry, there's another assumption here. So the assumption is that we've got a situation, we've got food, and every member of the population just randomly picks a site and tries to get food there. So okay, so you've got an M and N chance of randomly landing on food, but in addition to that, there's a chance that 2 members of the population will land on the food as well. Landing on food, but also a chance someone else has already landed on the food. Will also land and you will both starve. Right? There's only enough food in the site for 1 person, 2 people land on it, then you both starve. So what does that mean? Then that means that your chance of survival is M over N that you survive, minus the chance that somebody else lands on the food, right? And what's the chance that somebody else lands on the same square that you do? Well, it's going to be M over N, the chance that 1 member does, times the number of animals in your population. Technically times the number of animals in your population minus 1, but we're going to, because you don't get included, but we're going to assume that p is large enough that minus 1 doesn't matter. So chance, okay. So in this case, the chance then is the chance you find a food site, and this is the chance that somebody else also finds your food site. So this is the competition term, right? Okay, so if this is a probability, so then this is your death rate. Right? This is the probability that 1 member of the species will die. So then the total change is going to be dp/dt is birth rate times the number of elements of the population minus death rate. Times the number of elements in the population, or alpha p minus m over n times m over n times p. times p, which we could rewrite if we so chose as rp times 1 minus gamma over r. Okay, are there any questions? And if you have questions, or if you don't buy this explanation, do ask. We can pound at this a little bit. Yeah, it's not. I would say. Thank you. It's, yeah, I'd say this is like not. This was like not intuitive to me when I was first digging through the biology literature, and the fact that these linear terms, or sorry, that these quadratic terms appear. This is, the biologists do actually understand them, but it was taken as backgrounded knowledge. So and this is, I would say, this is kind of how you should understand a quadratic term whenever it appears in a differential equation, right? A quadratic term means that there's some probability that one member of the population will meet another member of the population, and that will cause either competition, so the removal, or reproduction, right? So the addition. Any other questions? Okay. So this is a very famous equation. This is the logistic equation. It's known as the logistic equation. And the standard form is dp dt equals rp times 1 minus p over k, where r is the unconstrained birth rate and k is what's known as the carrying capacity. And we'll see why in a second. Sorry, the unconstrained growth rate. I think it is. I don't remember what the Bernoulli equation is off the top of my head. But there's also, there's all kinds of equations that have different names depending on which field you're in. But yes, the Bernoulli equation just when you have a quadratic polynomial on the right-hand side. Okay. Okay, so the first thing to notice here is that this is an autonomous differential equation. And so we can take a second, we can look at its slope graph, but whenever we're presented with autonomous differential equations, or in general, whenever we're presented with differential equations, one of the first things that we should look at is, or we can do, so is try to get a global picture, right? So in this case, let's try to analyze this model before we solve it. Global picture. So in the global picture, we want to say something about the behavior of the solutions of this equation without having to solve them. And in particular, what we want to do is we want to see if we can classify the solutions and find any asymptotic behavior. So the first thing we want to do is find the equilibrium solutions. And the second thing that we want to do is we want to basically try to classify the behavior of all other solutions. Okay. So in the case of the equilibrium solutions, so to find equilibrium solutions, we're going to look for solutions with constant derivative, right? So to find equilibrium solutions, i.e. sorry, solutions. I'll just use P for the sake, since we're looking at the logistic equation. We want to find solutions P of T equal P naught, so just constant solutions. Find equilibrium solutions. We just want to look for solutions where okay, so if we're looking for a constant solution, that's going to mean that dp dt equals 0. Straightforward. So here, what does that mean? So what that means, of course, is if we have dp dt equals 0, well, we know what dp dt is. That's going to be r times p1 minus p. Okay. All right, so that's got two solutions. What are they? Rp equals 0, yeah. And so I should assume here that you're right to include RP, because it is entirely possible that R could be equal to 0. So excluding the case that R is equal to 0. So actually, maybe I'll just say, I'll actually include that because you're correct. So either P equals 0 or P equals K, or R equals 0. That's going to be the other case. Yeah, exactly. Okay. So here's then our picture. So we have T, and we've got P, and we've got K, and we have one constant solution here. So this is P equals K, and we've got another constant solution here at P equals 0. So here's our two equilibriums. No, so it's a good question. Thank you for asking it. So the question, sorry, is should be P of 0 equals P naught. And in this case, so an equilibrium solution is a solution that is constant everywhere. So this is a solution to the differential equation that is globally constant. So in this case, it will actually be P of t is equal to 0 and P of t is equal to k. Okay, so then something really nice happens. So for autonomous differential equations, let's just notice something, and then I'll state it as a theorem. So differential equations. Again, notice that the slope of the tangent line does not depend on t. dp dt doesn't depend on t. So in particular, we get three solution families in this case. In this case, there's three solution families. And I'm going to write them here in red. So the first one is if P is greater than K, then what happens? Oh, I should specify here. This is important. I apologize. I should specify here. Let's assume or r is equal to 0. So here, let's assume that r is greater than 0. We can do this whole analysis if r is less than 0. It's just that if r is less than 0, like this sign, actually, that's even important here. Unconstrained growth rate would add assume greater than 0. Otherwise, there would be this would be a plus sign, not a minus sign. And basically what happened, well, so what happens if we have unconstrained decay and competition? Well, everything just dies. It's not a particularly interesting case. So here, we're going to continue assuming that r is greater than 0. Then we've got sort of three solution phases. So if P of t is greater than k, then r p 1 minus p over k is actually going to be less than 0, right? Because p is larger than k, so 1 minus p is going to be negative. So this is going to be less than 0. And in particular, all the solutions are decreasing. So p prime is less than 0. Decreasing. I'm going to draw these guys on because I know what these solutions look like. But so you'll have to trust me for now. Second phase. So if P of t is less than k, maybe I'll do it this way. If 0 is less than p is less than k, then r of p of 1 minus p over k. Well, r is positive, p is positive, 1 minus p over k is positive. So this is greater than 0. So p prime is greater than 0. And the solutions are all increasing. So what does this look like? Turns out that that's what you're going to get. And then finally, what's going to happen if p is less than 0? So what are we going to get when p is less than 0? Should we? Okay, that's a very good question. Should we really care? No, not so. P is less than 0 is outside of the model domain. That is correct. But it's an interesting question to ask just from a mathematical perspective. There will be situations in which p, we're not thinking about a population or something. So it's good to ask from a sort of really understanding this model perspective. But you're absolutely correct that that p should never be less than 0. Yeah, but what will happen? Will the functions be increasing or decreasing? Yeah, strictly decreasing under our positivity. Yeah, exactly. Strictly decreasing under our positivity assumption for R. And I'm drawing these in because secretly I know what these things are. You will too in a moment. Okay. So this is really nice. I'm going to redraw this picture really fast. There's 3 solution families. And the solution families are given by the positivity or negativity of the derivative. Let's just say by the sign of the derivative. Of p prime. And in particular, so they're given by the sign of p prime. And the equilibrium solutions are given by the zeros of p prime. P prime equals 0. So in particular, basically we can actually, for autonomous equations, we can actually read the behavior entirely off of the graph of p. For autonomous equations, in particular first order autonomous differential equations. So p prime of t, dp dt is some function of p, right? So this is the definition of an autonomous equation, just written a little bit differently. The right-hand side doesn't depend on t, also that is the case. For autonomous equations, we can completely understand the behavior by understanding the behavior of f. Let me say it. Let me draw the picture and then let me try to say something about it. So for autonomous equations, what do we have? We have so we've got the picture that we had before. How do we draw them in? We've got our equilibrium solutions. P is equal to 0, and here P is equal to K. And we have, as above, we've got our, so we saw that we have increasing and decreasing and decreasing. These are different families of solutions, great. And if you notice, on the right-hand side, or we can also draw, so if we draw a graph here, here this is t, and this is p. We draw the graph of p prime. Let me draw it f of x. F not f of x, what am I saying? F of p versus p. Versus p, we can see all of these dynamics that we're seeing on the left-hand side on the right-hand side, right? So in particular, so here this is f equals rp times 1 minus p over k. Well, what's that going to look like? So this is a negative quadratic with zeros at 0 and zeros at k. And we see that f of p is negative, positive, negative. And so we see that p is decreasing, right? Since f is the sign of the derivative, or sorry, f is not, it's not the sign, f is the derivative, right? So if f is always positive in this interval, then f is decreasing, increasing, decreasing. Sorry, p is decreasing, increasing, decreasing. And there's a little theorem that says that this really does hold for differential equations, sorry, for autonomous differential equations. So that in this sort of beautiful way, we can look at f, we can draw a picture like this, and we can basically write down asymptotically in a cartoon sketch what the solutions have to look like. Okay, any questions? Okay, so I'm going to go over this a little bit, and then we'll take the break between starting on the lab. Or actually, I can just ask, who's interested in taking a break now, and who's interested in taking a break in 15 minutes? So who's interested in taking a break now? You could spit something in the chat. All right, we've got one vote for 15 minutes, so that's going to stand unless somebody else has something. Okay. Okay. So before I go into the classification of these things, let's just solve this. So I've drawn you some nice pictures. I've told you what has to happen here, but let's solve the logistic equation. See that I'm not lying. Let's actually like take a look at this behavior. So what do we have? dp dt is equal to rp1 minus p over k. How do we solve this? What's the simple way? Or not the simple way, but what's the of the methods that we know to solve differential equations, what should we do? We know like four, right? We know integrating factors, separation of variables, direct integration, and guessing and checking. Guessing and checking isn't going to work here. Integrating factors aren't going to work here because we have higher values of p. Direct integration isn't going to work because we have we don't have total derivative, and so separation of variables is going to be it. And we can actually, if you can solve it, you can always do separation of variables for autonomous differential equations. So in particular, this is going to be 1 over p times 1 minus p over k. I'll just use the shorthand, dp equals r dr. Whoa, sorry, not dr. What am I doing? dt. I'm going to rewrite this slightly. So 1 over p. So multiplying through by k with this. So let me rewrite the bottom so it's actually clear. P. And quick question: use partial fractions. You're anticipating what my next question is going to be, Anjali. I don't. By the way, if I horribly butcher the pronunciation of your name, please just let me know. There's no way I'll ever learn unless you tell me. So, yeah, okay. So we're going to use partial fractions. Solve. There definitely is this, when you take integral calculus as an undergraduate and you learn all these ways of solving things, and unless you then go on to take differential equations, there can just be a sort of like why are we doing this? And then you start trying to solve any differential equations. Oh, this is where this is all used. So solve with partial fractions. So the idea, just to remind you, we want to write k over p times k minus p as a over p plus b over k minus p. This is what we want. How do we do it? Well, let's combine these things again. So this is going to be a times k minus p plus b times p over p k minus p. And so then we just equate numerators. And what's that going to be? So we're going to get k equals a times k minus a b minus a p. Okay, when we equate polynomials, each term at each order has to be equal, because of course we can either think about that by, well, we can take derivatives and the equality needs to hold, or we can plug in sufficient number of values for p. And so in particular, so for this equality to hold, we must have that b minus a times p equals 0, and k equals ak. At least be consistent about which side. So this, of course, implies that a equals b, and this implies that a equals 1. Great. Sorry. Yes, that equals 1. So k over p times k minus p is equal to 1 over p plus 1 over k minus p. And partial fractions is one of these great mathematical tricks where we can just check, right? We can just multiply this out, and indeed it does work. Great. Okay, any questions? Okay. So now, what this allows us to do is rewrite the integral k over p times k minus p dp, or the antiderivative, as the antiderivative of 1 over p plus 1 over k minus p dp. And this is going to be internally consistent anyway. Log of p minus log of k minus p. And our assertion is that this is going to be equal to the right-hand side, which is RT plus C. Great. Okay, combining these logs, we're going to get, so P over K minus P equals RT plus C exponentiating P over K minus P equals E, RT plus C, multiply both sides through, P equals E to the RT plus C times K minus P. Okay, we're trying to solve for P alone, so we'll subtract P off. We'll subtract, sorry, P times E to the RT plus C off of both sides. We're going to get P times 1 plus E to the RT plus C is equal to K, E to the RT plus C. So finally, P is equal to K, E to the RT plus C over 1 plus E to the RT plus C, or of course we can bring down the C as a multiplicative constant, is, oh, yeah, or K times A E to the RT over 1 plus A E to the RT. Great. Oh. All right. So any questions about that derivation? So hopefully the only trick, right, was doing the partial fraction decomposition. Otherwise, it's basically an extension of what we've seen so far. But I want to take this though and draw our cartoon sketch again. So here's what we had. We had our solutions, P equals K, and P equals 0. And we claimed that some of them increased and some of them decreased, and then some of them decreased away. So first things first, we of course have to fix A. So getting A so that in terms of P naught is a little bit complicated here. It's not like the worst thing in the world. Well, actually, we could even, yeah, okay, well, whatever. So first things first, we do see something that's kind of interesting, right? So first, the limit as t goes to infinity of P is, well, T is going to increase much, exactly. T is going to increase much faster than 1, so it's going to be, great. So we're seeing what we see, or what we would expect to see here. There's one, so what is suspicious about this limit that I've just written down now? So there's something a little bit odd about it, and I'm curious if you can catch it, because I have done something that one needs to be a little bit careful about. I've excluded P is less than 0. Yes, that's exactly so. I mean, what I've said, right, in writing this down, it seems pretty clear actually that you know, that this limit really is just k. So then what's going on with all the p less than 0? Right? You know, I've made the claim that that in fact this goes down to negative infinity. And the reason here comes down to, you know, being a little uncareful up here, right? This guy isn't actually defined for p equals 0 or p equals k, right? So we have to be a little bit careful. And if we actually work out, so I should say, for p greater than 0, we see exactly what we'd expect. For p less than 0, the answer is going to be slightly different, and it depends on how we take off answer is slightly different. And basically, it is in this step. Be careful about removing the absolute value signs. So what you'll see is if you remove the absolute value signs carefully, if you just if you give this a negative coefficient and carry it through, then everything works out the way that you would expect. We could decorate that if we wanted. So this would then we would get a negative, and then things should, yes. Anyway, if you do it, things should work out as you expect. I wanted to sort of blow past that and then come back to it, because this is a really common mistake and it's very easy to make in these calculations. So often it sort of doesn't matter if you drop the absolute value signs. Here it really can. And you should check and make sure that the solution families that you get are actually the kinds of solution families that you would expect to get. This is the most common error. Okay. Are there any questions? Okay. So I'd like to do another example, but I may push that off till next class. So let's take 10 minutes, and then we'll be back then at, that's going to be 2 sorry, it's going to be 2:55 on my clock. Be 10 minutes from now. And in the meantime, I'm going to go through. I'm just going to quickly, or actually, before everyone goes, I'm going to quickly go through what needs to happen to get Google to work. And so, let me stop sharing for the moment. Sorry, look at the participants. Yes, fabulous. I'm a co-host. So I'm going to go ahead and share my screen here. And here's what we're going to see. Okay, so what you're going to see is that there's a new section called Modules. So instead of dumping everything in files, I'm going to dump them in modules from now on because I can't add a link to a file. And sorry for a moment, let me actually throw the chat on so I can see it. Great. So if you have a local installation of Python in Jupyter, then just download the IPython notebook, start it up, you should be good to go. If you do not, then click on this Colab link. It should try to open in a new window. Let it. And then you should be confronted, if everything's gone right, you should be confronted with this absolute catastrophe. There's going to be one difference is that you will not have an Open with Google Colaboratory button at the top. Instead, you'll have something else weird. So what you need to do is click this Open With, and then click Connect More Apps. And then you need to search for Colaboratory, and then you should be able to install it. Once you do, and it should just take a couple seconds, it shouldn't take very long. Then you should be able to hit Open with Google Colaboratory. And there you go. Now you've got your lab. Okay, so now, 10 minutes from now, we'll restart. So that'll be at 2:57 East Coast time. And I would encourage you to try this, and I'll just sit here and monitor the chat. And if you have any trouble, let me know. And I'm more than happy to walk you through the process. Although quickly, I'm going to grab some coffee. Okay. And yeah, so it should say Open With. So if you can see my screen right now. You should have, so if you click this arrow here, if you mouse over, it should say Open With. But it doesn't matter, it's just click this arrow and then click Connect More Apps. After install, we should have open with Google Collaboratory. There's only one ODE. Oh, so this is, you have to go to the modules, not files. So back here, under files, under week 2, there's only the one, because I can't add a link there, but if you go to modules, then this should be here. Yeah, let me know if you don't see it though, because I'm still learning Canvas, so for all I know, I need to like assign it to you guys or something. I have a quick question. I know they just decommissioned the Husky accounts. Do you guys have are you able to use your Husky accounts on any level, or are those just gone at this point? Okay, so those are just gone. You should have a new email, which is an @Northeastern email. It should be a Microsoft Outlook mail. Okay, I see. Oh, okay. So it's like okay. So you're not getting any new emails, and you can't log into a Google account with a Husky email. Okay, good to know. See, this is one of those things where it's like they just sort of did this switch over, and they didn't tell any of the instructors or advisors about it. So kind of trying to figure out what resources you guys have available to you. Yeah, okay, so that's good to know. In particular, because some of you, so those of you who signed up for the mentorship thing, I think several of you signed up with your Husky emails. And so I apologize because that's where that's getting sent. And so I'll try to fix that later today and get you hooked up with your mentors. So has anyone been able to successfully log in and see the lab? Cool. Thank you for letting me know. That's so it's easier to troubleshoot if I know that at least one person has been successful. You're using Jupyter Local, cool. If you're using Jupyter Local, run the first block of code, and it's possible it should actually format everything nicely. Although there was some update recently which broke all that. Yeah, the style block. It should what it should do is it should turn this table of contents into like an actual like Java menu, or JavaScript enabled table of contents. But I don't know. It was something that I put together a couple of years ago, and then I copied and pasted it through, and it seems like maybe it's been broken. But whatever. Yeah, okay. Well, it's fine. Maybe someday Jupyter will just add its own actual native table of contents ability. Okay, is there anyone that's having trouble getting the notebook working? Okay. So here's what I'm going to do. I'm actually going to use this screen because the tighter controls are a little bit easier to, or the tighter screen is a little bit easier to do over Zoom. Just go ahead and make a copy of this. And so what I'm going to do is I'm going to call this in class. And we're going to go through this and just follow along as we go through. And if you get behind, please just stop me, and we'll happily go over this with you and get you up to where you are. If for some reason you get too far behind, or you find something interesting and you're playing around with it, I will post the notebook that I'm working on to Google after the class is over, so that everyone can access it there. So if for some reason you do get lost, you will be able to recover what we've done. But okay, so let me blow this up. Is that good? Can everyone read that? Cool. Okay, so this is definitely would be better done with 2 monitors if you happen to have them. But, okay, so this is Jupyter, and Jupyter is an integrated development environment for Python and other things. It's been extended to quite a few things, but it's basically it's a nice system that allows you to annotate your code and write things in Markdown and describe what you're doing, while also running code in little blocks that you can save. So your typical way of doing programming is that you construct a script file, and then you compile that script file, and then you either run the compiled file or you feed it into a different engine that has the functionality for you. Jupyter is kind of like a large graphing calculator. It's a large Python-based graphing calculator. And basically, we'll be looking at a lot of examples, but before we even start, let's just demystify all this a little bit. So let's take this first block that doesn't do anything, and we show you how to do it if you go over onto this. Oh, sorry, I should say, the first thing that you guys should do is go to File and save a copy of this notebook in the drive. Because otherwise, one of 2 things will happen. Either the worst thing that'll happen is we'll get through this whole lab, and then you'll close the window and you'll lose all the work. The other thing that can happen if I screwed the permissions up, and I don't think so, but we'll see, is that we could all be editing the same notebook, and then hilarity will ensue. Okay, yes, should be fine. But so Jupyter notebooks work in blocks, and blocks are pretty easy to manipulate. You can add them, you can delete them. There we go, block's gone forever. If you want a new one, you can click new code block or a new text block. And if you want to see how anything that I've done is done, you just double click on it, and there you go. This is the markdown. Does this? Yes, yeah, so the 2 files are exactly the same. They are just, Google just renders things slightly differently. So if you downloaded it, it should be exactly the same as the one over on the Google Cloud. So similarly here, oh yeah, and the file is the same. Yeah, it's the same file in the module and in the set of files. I just mirror them. So yeah, and so you can write everything in Markdown, and it's actually quite nice, especially for those of you aspiring LaTeX folks. You can write straight into tech here. So, if we want to say, how do we solve fraction d t, well, it's equal to r times p1 minus fraction p. Okay, do that. There we go. And you know, there's some special functions and some weird stuff that you won't find in here, but it's pretty good. It uses the same LaTeX, I think it's MathJax that MediaWiki uses. So basically, one of the things that's great about Jupyter Notebooks is that they allow you to just do all kinds of stuff with your comments. You can include pictures, you can format things nicely. It's great. And so actually, as a first thing to do, if you're here, go back up here quickly and add a code block. And if you're on this side, you can just add a code block. You can also add code blocks by hitting Alt-Enter. And so here's some of the functionality. So, you know, in the sort of graphing calculator sense, you can go, okay, so what's 2 plus 2? Great, okay. And then to run the code block, you either hit the arrow on the right-hand side, or you can do Shift Enter to run the code block. And it should be Shift Enter on a Mac, and I think it's it's not Command, it's Alter Option on Mac to add the new code block. Yeah, 2 plus 2. Yeah. 4 minus 6. There we go. Great. We can store things in variables. So y equals 4 minus 6, and then recover y later. Minus 2. Fabulous. Okay. So it's one of the nice things about Jupyter is that you can basically you can do a lot of playing around. And if you ever want to play around with something, first, don't be afraid to just completely screw this notebook up. You can just download a new copy. Doesn't matter. But second, you can always add a new code block and start messing around with things and seeing what happens. Okay. Are there any questions so far? Okay, so we're doing mathematical modeling in this class, which means that, yes.
The question is that because I cannot open it through the camera, so is it fine if I just open it through like the website, I think?
Oh yeah, absolutely. You should absolutely open it through through Google. The only reason that I'm not showing the Google version is because I found that we could go through it. It's exactly the same. I just found that doesn't look as good coming over over streaming.
Okay, because I haven't downloaded like the Jupyter or something. I never used that before, so I just want to make sure I can do that also. Okay.
Absolutely. Thank you for checking those. But yeah, it's totally fine. And everything in this class will be mirrored on Colab. So if you want to do Jupyter locally, great. If you want to do it on Colab, you do it there too.
Okay, thank you.
Yep. Okay. Any other questions? All right. So so basically we're doing mathematical modeling. So we're going to be using NumPy, Matplotlib, and SciPy a lot. When you start doing machine learning, if you go that route, you'll be using TensorFlow and scikit-learn a lot. If you basically you're going to have a sort of a standard set of libraries that you always just start every new Jupyter notebook by including. And for us, it's basically going to be NumPy and Matplotlib and ODE for this class. So what NumPy does is NumPy basically gives us the tools to deal with matrices and mathematical functions. So for instance, if I try to say sine of 4, Python goes, I have no idea what you're saying, right? Name error. Name sine is not defined. Okay. So NumPy is going to give us mathematical functions, and it's going to deal with matrices for us. And it's going to deal with matrices very nicely. Matplotlib is going to allow us to produce plots. And it's basically, the syntax for Matplotlib is roughly the same syntax as MATLAB's plotting syntax. There's a few differences, but it's pretty close. So if you're comfortable with that, or if you've used that before, it should be pretty familiar. And then ODEInt is going to be our ODE solver. And ODE is basically going to solve ODEs exactly the way that I talked about before. By, we're going to give it some initial condition, then it's going to draw a little line, and then check, or it's going to compute the derivative, draw a little line at that slope, compute the derivative again, draw a little line at that slope, and we can actually see it happen. So the first thing that we're going to do then is say from the SciPy library, so Science Python, import ODEInt. Then from MATLab's Matplotlib's pyplot library, we're going to import Matplotlib's pyplot library, and we're going to call it PLT. And that's going to keep track of all of its functions in PLT. And then we're going to import NumPy as NP. All right. And we're just going to jump in, and I'm going to teach you, if you haven't done any programming, I'm going to kind of teach you as we go. If you have, a lot of this is going to be pretty straightforward, but hopefully there'll still be something interesting. Okay, so we want to solve a simple differential equation. Oh, you don't have SciPy. Okay. Sweet. Yeah, so thank you. If you don't have SciPy, you can pip install SciPy through Anaconda or whatever your package manager is. Cool. I will hold on for a second. And then just restart your notebook. You just do that kernel's restart. It might not even be necessary. Sometimes it'll load in just fine. Okay. But so we want to solve a differential equation, right? dy dt equals minus kyt. And we want to do it for a particular parameter value. So of course, one thing that's going to be true with numerical solvers is that we can't do the kind of global analysis that we've been doing by hand. Numerical solvers need everything specified for them. They need to be told exactly what they're doing. Computers are dumb, right? Computers will do exactly what you tell them to, whether you think that that's what you're telling them to do or not. So the way this is going to work, and Sai, I'm just going to jump on. I'm just going to keep going, but I'm more than happy to jump back when you've got SciPy installed. So if we want to use ODEInt to solve this equation, then what we're going to have to do is we're going to have to write the right-hand side as a function called a model. We can actually call the function anything, but in general, model is going to be a function of three things. Y, t, okay, this is our standard differential equation, and any parameters that we want to give it. Okay, so let's define our model. And I'll just type the code out here. So defining a. So the way that you define a function in Python is with the def command. So def, and then we give it a name, some name. In this case, we'll call it model. And then we tell it what variables the function is going to take. Okay, y, t, and k. And but we can also, if we do this hash, it adds a comment, and it means that Python won't try to interpret it. We just say whatever we want. Note, the order here is really important. It must be ytk for ODEInt to work. Basically, ODEInt will always treat your first variable as if it's y, and your second variable as if it's t, and your third variable as if it's some parameter. So if you switch them, weird things will happen. Okay, so then what do we want to do? Well, this model is supposed to basically compute the derivative for us. So if you give me some y and some t and some parameter k, it should compute the derivative. And what is the derivative? Well, the derivative, dy dt, so we'll call this a new variable. Dy dt is just a variable. We can call it whatever we want. Dy dt is minus k times y. T doesn't actually even appear. And then, so we'll compute that. So you give me a y, a t, and a k. I compute the derivative by multiplying k, sorry, minus k by y, and then I'll return dy dt. And there we go. Here's our model. Any questions? Okay, and so again, this is just a function, right? So for instance, we can like play around. Let's just put some numbers in there, right? So if y is equal to 4 and k is equal to, I'm sorry, t is equal to 0 and k is equal to -1, this will then compute for us, right? What is this computing? So this is computing dy dt equals minus k y equals 4, oh, sorry, y in this case is 4 minus -1 times 4. Great. There we go. And we can do this with any other values, right? And so if we throw -2, well, okay, then we double k, then we get 8. 1. What happens if we change t? Nothing. Because t doesn't appear on the right-hand side of the equation, right? Because this is an autonomous differential equation. So in this case, t does not, the model does not actually return anything for t. Okay, any questions? Okay. So feel free to like play around with this, run it for some values and see what you get. All right. So again, we have to make everything very, very specific in this case. So we've defined our model, right? And this is just a function that returns the derivative. So let's set our constants. So in this problem we want to solve, we have k equals 0.3. And let's set y naught equal to 5. You also set it to 0 or something else. So this is going, y naught is of course going to be our initial value. Okay, so then again with the being very precise. So t for us is not going to be some continuous parameter, right? T actually needs to be a list of time points that we want to evaluate the function. Because essentially, again, it's just going to draw a bunch of straight lines and connect them. And so there's a lot of different ways to do this, but one nice one is NumPy has the library linspace. So what linspace does is, so if we do np.linspace, is it'll just return a list of evenly spaced numbers between some initial number and some final numbers. If we want to go between -1 and 1, for instance, here we go. It's just going to return 50 numbers evenly spaced between -1 and 1. If we wanted to do -10, and I don't know, computers can handle large numbers, there we go. 50 numbers evenly spaced between them. If we want more than 50, we can say number equals 100. Okay, 100 numbers evenly spaced between the start point and the end point. Or if we want less, we could have 10 numbers. There we go. So in general, what we want to do then is we're going to define t by giving an explicit set of time points in our domain. So let's say we want to start at t equals 0 and go up to t equals 20. And let's actually start with a small number of time points. Let's start with 5. Here. You can print variables off using the print command. We'll do that a little bit in a second. All right. So I've got 5 points evenly spaced between 0 and 20 at 0, 5, 10, 15, 20. Great. And so now we actually want to solve the equation. But let me pause here. Are there any questions? Okay. All right, so now we'll feed all the pieces. So we have a definite function, we've got a definite start point, we've got parameter values for each of our parameters, and we know the time points that we want to solve the equation at. So let's go ahead and solve it. And this is the form that it's going to take. So we want our solution, actually, before we even do that, so it's just going to be ODE int, then we need to tell it our model. We need to tell it our initial value, which was y naught. And I'll just actually copy these in. And let's set up our time. So np.lin space. This should all be set up for you. So don't worry. 0 to 20 with 5 points. And so the order of these things is very important. It's always first the model, then the initial point, then the time steps. And then since we want to specify k, we're going to say args equals, and then we put in our value for k. Now, just to be clear, and here we go, ODE helps to spell it correctly, is not defined. Okay. This is why I picked 5, isn't it? There we go. All right, let's start at 5, at y naught equals 5, not y naught equals 0. Okay, so just to be clear, I've done this all in terms of variables, but I could just plug the numbers in here if I wanted to, right? What's our initial condition? Well, it's 5. And what is our value for the argument? Well, it's going to be 0.3, and look, we get the same numbers. It's kind of, you set it up here, then sort of you can add some comments. It is defined for y equals 0. It's just 0. And the reason, right, is because this is the exponential decay function, which has an equilibrium solution at 0. So it's perfectly well defined. It's one of our like great special generic cases. It's just not. It's just not something that we need an ODE integrator to solve for. Okay. Any other questions? Second problem. Yes. Oh, yeah. Right. So yes, the solution. I think Sai's question being is the solution to problem 2 of week 1 just that it's a 0 solution, and that is correct. This does happen. Okay. So the next thing that I want to do is, so I've got this list of numbers. So let's save it as something. All is equal to ODE int. There we go. And again, so I said it here, but like, oops. I can compute something in one window and then hold it in a variable for another one. And we can determine basically the information about what the shape of the array is. So if you notice, this is an array, and it's being written as a column vector, and it actually is, right? So the shape here in coordinates is that it's a 5 by 1 matrix, right? So it's 5 rows, 1 column. Okay, so the next thing that we want to do is we want to actually visualize this. And so we're going to use our PLT, so our matplotlib, plot, ysol, and here we go. Here's our first little linear approximation to a solution to a differential equation. Okay, so there's 2 things that are incorrect about this plot, though. So the first one, of course, is that, well, okay, this isn't really the solution to a differential equation, right? It's like it's numerical approximation, and we can see that by how jaggedy it is. The second one is that if you notice, the horizontal axis is not correct, right? Or the scale isn't correct. So what is being plotted on the horizontal axis here is just basically the position within the array. So this is the 0th position is 5, great. The first position is 1.1, or I should say position 0 is 5. Position 1 is 1.1, position 2 is 0.024, etc. No, it shouldn't be smooth. It will, yeah. So you're absolutely correct. It will never be smooth. It will always be a numerical approximation. But we can make it smoother. So one thing we could do, of course, is instead of having 5 data points, we could up it to 20. Okay. So if we up this to 20, and here I'll just redefine, so t is equal to np.linspace 0 to 20. Actually, let's just go to 100. Great. So now I've got this huge array. And let's plot it, plt.plot. And there's a nice smooth curve, right? Or smooth looking curve. And it is genuinely a better approximation as well. The second thing, though, is that, again, now you look at the scale at the bottom, right, has gone from 0 to 100, even though in theory, t is still from 0 to 20. So if we want to plot t versus y, we just need to specify it. Plot t versus y, and all of a sudden everything is also scaled correctly, right? So it just lines up the time points in t with the y solution points in ysol. Any questions? Has an upper limit of 100. Did you? So probably because you plotted ysol. And so ysol, the x-axis is just going to be the position of the data point within the array. If you throw a t in, so if you plot t versus ysol, then it should be against the, it'll use the values in t as the time points for x. Yeah. Okay. It's I mean, the number of times I've made that mistake, like in serious projects, like is shocking. Yeah, as long as you don't, present it to somebody as fact. Okay, but so this is like, yeah, so this is like it really in a certain sense. Like ODE is actually shockingly easy to use. If we just give it a model for the derivative, then it'll do a lot of the work for us. Okay. So let's look at another example, right? So let's say one of the things that we could do, right, is we could use this to look at different parameter values. So as we see below, I could say, well, what about ODE int? So if I want to check my model for, well, pick the same starting point, y0. ODE, so yeah, it's a good question. ODE int, I think it is only a linear ODE solver. There are nonlinear ODE solvers that you can use, but ODE int is a pretty straightforward linear ODE solver. You can actually check. So if you have any interest in this sort of numerical analysis side of this stuff, there's a whole bunch of different algorithms that these things use, and ODE int, if I remember right, uses it uses the ASOTA, which is an old Fortran algorithm. But you can really kind of dig deep into how these things work. But yeah, so then in higher order differential equations are harder, and PDEs are harder still. And we'll see that as we go farther in the class, that things can really go to hell pretty fast with PDEs. I mean, they can go to hell pretty fast with ODEs. We'll see that here in a second. Okay. So let's say that we want to check things like for different parameter values. So for instance, we could do set our k equal to 0.3. Oh, yeah. Set y naught equal to 5 again. Okay. And so we can even, if we want, it's a little, we can just plot it and then feed the values, so we can compute it and then feed those values straight into the plot. There we go. We can check it for different values. And what we'll find is that they all look shockingly the same. And that's, of course, because our access is being scaled here. Not exactly the same, but they're pretty close. So if you want to plot multiple plots on the same figure, then you just add multiple plot calls in the same line. And there we go. It'll kind of take care of everything for you and do all the coloring. The standard behavior of Python, of Jupyter Python, is just to add to the next plot. Any questions? We could also do things like change our initial conditions if we wanted to. Not change k, but check what happens if we go 5, 3, 1. And we're starting to kind of see these diagrams that I was sketching out, where we get the same asymptotic behavior. So here I do the same thing and just plot them all. Lose somebody. Oh yeah, of course. Starting at 0. Let's make our y naught equals 5. There we go again. And there's all kinds. So PLT plot it's a great tool. We can do all sorts of things with it. So of course, when we do this, we would really like to do something like, you know, a bit more on the last argument. The k. Right. So remember the k here is it's the term that if we integrated it out would become the exponential, right? It's e. This is e to the minus kt are the functions that we're plotting. And so the way it's incorporated into the model, right, is the derivative is dy dt is minus k times y. So as we change y, in particular, we can see it here, right? So remember, the solution is actually going to be y of t equals c a e to the minus k t. So you have the more important question that I'm just completely glossing over, which is why. So right. So quickly just finish this up. So of course this is going to be. This is going to be our y naught, and this is going to be our k. But Sai has a different question, which is why did I put the comma after the 6? And the reason is because ODE expects what's called a tuple object. So there's all kinds of different objects. We'll talk about them as the class goes on. There's different kinds of collections of objects. So there's lists, like a list, 1, 2, 3, 4, 5. Also, np.linspace from 1 to 2 returns an array. And then there's something called a tuple. And a tuple is an ordered list that is it's a slightly more basic object, and ODE expects a tuple. And there's this one weird quirk of tuples, which is when you put a single number in one, you have to put a comma behind it. And so if you take this comma out, you'll see ODE completely breaks and says extra argument must be in a tuple. Okay, great. We can play nicely with it. Good question. Thank you. I forgot to mention that. So again, how it applies them is it just if you have multiple, we'll do multiple in just a second. But it just does it ordered. So it kind of doesn't leverage Python's nicer features, unfortunately. Okay, so quickly, of course, when we do something like this, you know, it would be nice to, for instance, you know, be able to label the axes with what the k values are. So in this case, k1 is 0.3. We could label k2 is 0.7. K3 is 1.1. And then we can just add a legend with plt.legend. And there we go, just adds them right there. And we can, you know, these could be more complicated labels, k equals. If you're comfortable with playing around with strings, you can add strings. There's also all sorts of nice things if you want to add a title. Title. Solution to. I wonder if this will work. Let's go. So there's a little bit of LaTeX that you can use in the titles here. P equals minus kp. There we go. Solution to p equals minus kp. There's all kinds of stuff you can do. You know, the possibilities are, you know, you can change the markers, you can do all kinds of great stuff. Change the line width, the colors, set your X labels and your Y labels. In general, you know, you should follow good graph making etiquette and always plot, you know, always label your axes, and if possible, give the thing a little title to state what it is. And if you have multiple lines, you should try to add a legend unless you have, you know, too many. Okay. Any questions? Okay, so let's look at some examples really fast. So let's say that we want to do a more complicated function. We want to solve dy dt equals minus y plus k. Well, okay, we just need to define a new model. We want to solve it for t between 0 and in the domain 0 and 5. And we want to plot the results for k equals 1, 2, 3. So what if you have more than one constant? Yeah, so I'll say what to do in just a second. So actually we'll do it down here. Do it down here? Do it down. No. Okay, well, I will say it here then, because apparently I don't say it down there. So if you have more than one constant, so the way you do it, here, I'll show you here. So let's say that we wanted to do this. K minus j times k. Great. So we'll define our model. And we always need it to be y, t, and then our constants. So in this case, jk. But y always has to go first and then t, and then whatever constants we want. So dy dt is going to be minus j times y plus k. And then we'll return dy dt. And it doesn't hurt to check and just make sure that this works. 1, 2, 3, 4. Great. Okay. Got something. For those of you who aren't that used to programming, if you do something like this, which of course would make perfect sense mathematically, you'll get a massive failure. And the reason is because it thinks that jy is a variable, right? So it goes, name jy is not defined. Python actually generally has pretty good error messages. So always go look. If you do get an issue, it should tell you exactly what line it's on, and then give you somewhat of a descriptive error message at the end. Okay. So just do this, what are we doing? Testing. Oh, and I should have done this before. Let's call it model 2 so that we can keep multiple models around. All right, so then do ysol equals ode int. I like setting up the variables beforehand. So let's just do j equals 1.0, k equals, what did I want k to be? Well, let's just start with 1. What should t be? What should t be in accordance with the problem? NP lin space, and then what should the ranges on the lin space be? Yeah, I agree. So t is between 0 and 5, and so the lower bound is 0, the upper bound is 5, and then we can pick how many data points we have. Let's do 100. And if you want, you can do 1,000 to them there. Okay, we'll do ODEant, put our model in. We put in, what is our Y naught? Our Y naught here is 0. 0. Y naught. Then we put in t. And then we'll have args equal. And so what this will do now is it will feed in what we just give it a tuple or of arguments, and we'll just feed them in order, right? So if I do kj, it'll feed k into the j slot and j into the k slot. It's not what we want. It's jk. And so interesting quirk about tuples, we can throw. And it's not even that. It just basically assigns the first entry to the it just assigns whatever the first entry of the tuple is to the first variable, and the second entry of the tuple to the second variable. Yeah, I guess no, yeah, a little bit like a dot product, except we don't add them all up at the end. Yeah. Yeah, and then so with tuples, you don't need the comma after if you have more than one element. The one element, basically, the reason for the one element thing is because this is kind of ambiguous, right? This could just be a parentheses thing and doesn't specify that you're trying to define a tuple. T dot plot ysol. Boom, there we go. Here's our solution. All right, and now this thing wants us to do it for k equals 1, 2, 3. So copy and paste, k equals 1, k equals 2, k equals 3. And there we go. Here's our solutions. Okay, so we have a computer, and so we shouldn't just be copying and pasting things. Anytime that we copy and paste things, we should just automate it. And the way to automate things, one of the ways to automate things in Python is to use what's called a for loop. Loops work a little bit differently in Python than they do in a lot of other languages, and it's something that you may love or may hate. Personally, I kind of like it. But basically how a for loop works is we say for some variable, whatever it is. What do I say? Oh, I'm sorry, this shouldn't be equal. This should be n. Disaster. Okay, so for k in, and then you just give it a list of values it wants to take on. So for instance, 1, 2, 3. 1, 2, 3. And then do something. So in this case, what we'll do is have ysol equals ODEint for j and k, and then plot it. And it will run through. And so what it does is it goes through this chunk of code for k equals 1. Then it goes through it for k equals 2. Then it goes through it for k equals 3. And we can continue on for k equals 4, 5, 6, 7, 8, 9. So it's quite nice. And in fact, so in this case, what it's going to do is it's going to go through this list and assign it values. You can also do for k equals 1, then 10, then 100. And there's an even sort of more sophisticated way. We could also loop through any other list-like object we might have lying around. So for instance, if we wanted to use np.linspace and say, well, let's do 50 numbers between 0 and 20 for our k values. There we go. So for loops in Python work for basically anything. Like, it could be the number for cat, the word cat, and then like a time object if you wanted. But it makes automating really fast, right? And anytime you find yourself copying and pasting code more than once, you should probably just put it in a loop. Okay. Any questions? Yeah, so the important thing about the structure of a loop is that all of the indented stuff is the stuff inside the loop. And this is how Python works. So all the indented stuff will be inside a loop or a function or something. Okay. So yeah, I would say do this little exercise, right? So we've been changing k around. How would you change y naught around instead of k? All right. So this last thing, or the next thing, we can use numerical equations to solve more complicated functions. So we'll define model 3, and we need a y, a t, and a k here. It's supposed to give a derivative, so dy dt is going to be equal to minus y plus k times sine of t, and then we will return dy dt. And if you just hit, enter, it will happily define the model for you. So it's always worth checking and making sure that your model actually works. Just go, 1, 2, 3. No, the model is broken. It says one missing model requires positional argument k. Oh, sorry, it's because I'm not using model 3. Okay, no, the model is broken. And the reason it's broken is because sine is not defined. There's a lot of the mathematical functions that you think you might want are defined somewhere. They're just usually defined inside numpy. Okay, but once we define it, then we're set. And so then we can set k equal to 1. And with this problem, we want to plot the results for different values of y naught. So the way we're going to do this is we're going to say, well, for y naught in range. So I talk about range up here. Like linspace, range will just compute the integers, or just give you a list of integers between two values. So for instance, minus 5 and 5. And so then what do we do? Well, y solution equals ODE int model y naught t. Let's tell what t is supposed to be. T in space 0, 20, called data points. Args is going to be k. We only have one argument, so we need to put the comma back on the side of the tuple. And plt plot t. So, oh no, what have I done? Positional argument k. Oh, actually do it for the correct model. Here we go. So we see this kind of interesting, nice, fact that for this differential equation up here, for this y plus k sine t, actually what happens is it sort of doesn't matter what our initial conditions are. It all eventually decays down to, all solutions decay down to a sine function. And this should give you some kind of, the picture here that you might be sort of scratching your beard and thinking about is this is kind of similar to our like Burley-Griffin example, right? Where we had the variable inflow that was given by sine. All right. So just a quick trick for those of you. In Python, you can turn a number into a string by doing str and then So even though y0 is 4, the string will now give you the number 4. So if you want, you can do label equals something like y0 equals. And then the way that concatenation happens in Python, so you have two strings. So like this is a string, and you add them together. No, it's not. It will concatenate them flat. It won't add a space or anything. So here you go. This is a string. No, it's not. If you want to add a space or something, you could add it like this. So if we do this label plus str, throw in our y0, and then at the very end, we'll do plt legend. Then it will actually construct the legend for us and place it in an incredibly inconvenient location because it's doing it automatically. But what are you going to do? Okay, any questions? So, and that's kind of it. And so I would say, play around with these a little bit. This is definitely an interesting equation to play around with. And we can even, set up the model domain here a little bit. So define model 4. We have two parameters now. So we're going to have y, we're going to have t, we're going to have a, we're going to have b. dy dt is equal to a times, so now we've got a t involved here. And as a final quirk of Python, which I'm sorry, I should have something about here, Python does not use the caret as an exponential. Instead, it uses double stars. So in this case, this is what we would have here, times y times t. Okay, so this now is a non-autonomous differential equation. It depends on time. Return dy dt, but that's fine as far as ODE int is concerned. So if we set our t equal to np.lin space 0 to 20, and then plt.plot t ODE int of model 4, our initial y0, let's so y0 of 0 equals 1 is what we want. Then we put in t, and then we are going to have args equals, we've got two of them now, so we don't need to use the trailing comma. We're going to have a equals b, and let's have a equals b equals 1. So a equals 1 and a equals b, and then we'll call it ab. We plot, and we have misspelled linspace. Misspelled. There we go. Then we get some kind of solution like this. And we can ask ourselves, so what happens as we go from -10? Well, same thing. Okay. 10. So what happens if we start increasing b? Increasing. Going negative, and all of a sudden everything blows up, right? So let's go down to, say, 0.1. Then the sign flips. And eventually this blows down to -infinity. And eventually this just blows up completely. So this is entirely possible with ODE solvers, any sort of numeric solver, even if the function or the differential equation actually has a nice solution. It's just entirely possible that the thing will blow up and you won't be able to find it. And I would definitely just, and the reason for this, of course, is that it can basically, since it is discrete, it can just wind up jumping on bad values that make it continue to explode, even though if it was continuous or a little bit better, it would actually, those values would sort of tamper out. This can wind up being a huge problem in things like optimization and complexity. thought there's some fun values in here. I don't know which one they were. Cool stuff happens. 10. Yeah. But yeah, but basically, you know, the great thing about ODE solvers is that you know, you give me any differential equation and I can give you a pretty good solution, especially a pretty good solution as far as like what anyone would want to do. You're getting an issue. What is the issue? It's because you have a second equal sign instead of a minus sign. No worries. This is, yeah. Anyway, okay. So how does this lab finish up then? So I would suggest that you go through it and answer all these questions. Take a look at this one. This requires if and else, which we won't use that much in this class. But so here's the Lake Burley Griffin example once again. And as an exercise, we can actually just go through and simulate this thing. And I would encourage you to do it. I will kind of finish off the lab for you. And you should get that kind of nice picture that I showed you before. I might have it sitting in here somewhere. Anyway, but you should get that. You should get that nice picture that I showed you before. And so the homework assignment for this week is going to start right below this line, and is the case study "It's a Dog's Life." And this is one of the case studies from the book, where they were looking at basically, here's the paper if you want to have a look at the original paper, but they were looking at the dynamics of animal control in Mumbai, I think is where this was originally. But there've been different cases. There's been several of these studies done in India, and there's been several of these studies done in Baltimore. Is another one, where basically the question becomes, how do you model something like the population of stray dogs to try to get some sort of accurate handle on what kind of solutions you could present to the problem? And one of the great things about successfully modeling something is that then you can try to model solutions and throw a battery of different solutions at a problem. And so in this case, so there's a couple of solutions that are going to be explored here. So the first is going to be a euthanasia solution. And the second is a rehousing solution. There's also some solutions like sterilization and various other things. But in this assignment, we're going to be looking at euthanasia and rehousing. So if we start with a standard logistic equation, right? So this is density dependent growth, where we assume that the dogs are competing for resources, probably food, and if there's enough of, and if there's enough of them, then the growth pattern levels out. We want to go through and add a term. So we say, okay, so what if, to incorporate euthanasia, we're just going to assume that at each time step, a constant proportion of the dogs are euthanized or removed from the area. Then we can add that term in by just subtracting off again, since it's constant number, subtracting off a constant linear term. And so what you guys are going to do in this assignment, so unlike assignment 1, assignment 2, the entire thing is going to be one sort of model here, is to go through and solve this differential equation by hand. So there's going to be some analytic parts. Then we want you to simulate it. So we're going to give you some initial conditions that were pulled from some studies in Baltimore in the 70s, and simulate it. And through the simulation, basically, we just want you to explore the logistic equation a little bit and see if you can figure out what some of the parameter values are doing, especially now that we've added this epsilon term in. And then I actually want you to say something pretty concrete about it, right? So just in the same way as we did, and we'll do another example of this on Wednesday, but in the same way as we did looking at the logistic equation, try to really like spin out. So what is like the space of all solutions and what are these parameter values doing? You're going to analyze this sort of extended logistic equation. Okay, formally it winds up being the same as the logistic equation and do the same thing. Then you're going to take a look at a rehousing model, where it's a fixed number of dogs each year are rehoused, and do the same analysis. And then the final part of this lab is to basically look at our two models and try to really carefully say what exactly you should do, right? Think about what are the virtues of these models and how would you use them? If I give you some initial conditions, can you actually solve these models to figure out, how much energy you would have to put into euthanization or rehousing in order to control the problem? And how do you compare them? And then as a bonus, and I would really like everyone to take a crack at the bonus problem, because this is really like where the rubber meets the road with the modeling, right? We can consider this combined model, right? So this is if we have both rehousing and euthanasia. And we have some cost model, right? So how much does it cost actually to rehouse, and how much does it actually cost to euthanize? Then the big question is, what is the most cost-effective combination of euthanasia and rehoming that will eventually diminish the population to zero? That is kind of the goal of this lab, to figure it out. But I'm doing a bit of an experiment in this lab with you guys. So I haven't run it in this way before, or this homework assignment. I haven't run it in this way before. And so I really want to encourage you, again, don't answer people's questions, but if you have clarifying questions, if you are having trouble getting started on one of these problems, do ask, and we can definitely talk about it. So I would like, hopefully this will guide you through, and we'll get a little bit of feedback on it and make sure that like the questions are clear enough. And in future iterations of this class, I mean, what I would like to get is where this is not a bonus problem, but this is really something that everyone can shoot for. But for now, for you guys, it's a bonus problem. Okay, so what I want you to do to actually submit this homework, because there are two parts. So there's some simulation and there's some analytic. And you can either do it all in this Jupyter notebook, right? So how do you solve this problem? Well, to solve, we use, separation of variables and solve it out in here. As far as I'm concerned, you can just turn in, as far as I'm concerned, you can turn in the Jupyter notebook, provided all of your answers, your simulations are in there. If you do that though, please write an explanation of what I'm seeing in every question, so that I know what's going on. You are also more than free to do the analytic problems by hand and turn those in separately, and only include the two computational problems in the Jupyter notebook. So either what you turn in should be an entire Jupyter notebook, which is the entire assignment, or it should be a Jupyter notebook with the computational parts and and a PDF with the analytic parts. Okay. Are there any questions? And it's a lot of information at the end of a long lecture. No, thank you for asking. No, the Lake Burley Griffin case study is not part of the assignment. That's for your own edification. Okay. I would also say, I would really encourage you, you should be able to do this assignment after today's lecture. We will do a little bit more of this kind of analysis of these equations, but you should be able to at least get started. And I would recommend starting a little early on this one. This assignment is, I think, conceptually harder than the first one. The first one is a little bit more straightforwardly we'll just do the things that we did in class, but here's like another example of them. This one takes, there's a couple of these questions take a little bit of thought. And I would also encourage you guys to, to post on the forum about how you're thinking about these questions. All right, are there any questions before we? Ooh, invalid syntax error. Is that in, are you on Google Colab? I don't think so. That should work. So you're on local Jupyter. Maybe you got the wrong $sign. Let me check. That's very weird. Oh, yes, you will need to pick. So here, you will need to pick. Thank you for asking. You will need to pick values for epsilon to solve numerically. Yeah, and I want you to do that because that's actually a skill, right? And I want you to be careful about that, right? I say it here: write a reasonable estimate for the initial conditions given the information in the case study, right? That making reasonable estimates based on, for your parameter values based on the initial conditions is non-trivial. And it is an important part of doing mathematical modeling. So just always state your assumptions. I think that I may have figured out the issue. There we go. Okay, so the issue is that you have, but thank you for asking about that. So Zihao, the issue is that you're pasting into a code block, not into a markdown file. Sorry, not into a markdown block. So in order to fix it, go to cell type, markdown, and then it should interpret it as markdown. Yeah, no worries. Any other questions? Cool. Well, if you have any other questions, do not hesitate to ask. And I would also say, so most of the things have been going on the forum. I don't really have official office hours for this class right now because I'm trying to answer things through the forum. But if you would like to chat, especially with some of the coding stuff, it can be significantly easier to just have me look at your code, or to spin up a whiteboard and just have a place to talk a little bit. I'm more than happy to jump on a Zoom call with people of basically any time. Just we may need to schedule something a little bit beforehand, but just shoot me an email, and I'm more than happy to go through anything with you. So, all right. Good luck, and let me know if you have any questions, and I will talk to you all. We are following the same schedule for class hours. I'm still trying. There is a last question. Actually, maybe I will just poll everyone here. I made screwed up the. So I guess here's the question. If the question is just in. I feel sorry for everyone who's here right now. Who would attend? So if I did double this class basically and cut down the length of this a little bit, and then yeah, if I cut down the length of each class a little bit, but then I just doubled. So I just taught 2 classes with exactly the same content, but I taught one of them at, I said the wrong time in the quiz, and I apologize. If I taught one of them from 9 o'clock to 11 o'clock p.m. Eastern Daylight Time. So I think that should be 9 to 11 in the morning, Beijing time. Who would attend? who would attend the morning class? It's one. I mean, unfortunately, probably some of the students that would attend are not currently in, because we are missing 3 students, and so probably several of them are not in the current class because of that exact reason. So just say it again, yeah. So who would be interested in attending from 9:30? Sorry, who would it be interested? At 9:30 to 11 p.m. EDT. Well, I will send out an email to, I'll send out one final scheduling email to everyone just to make sure that we also get the students that aren't here. And if we have a quorum, I think that a quorum is going to be 4. Then I'll run the classes in the morning. And if not, I am more than happy to, I'll just run, I'll maybe try to run an office hour in the morning for you guys. So that we can at least have a quick an opportunity to, for everyone that is watching the lectures, instead of attending them live, to ask questions that they have. That might be the solution there. Okay. All right. Well, fabulous. And I will see you guys on Wednesday. And please let me know if you have any questions. Yeah, well, so I would continue running class at this time. This would just be in addition to the current class. Yeah, there's a great website that allows you to it's like when can we meet with time zones, that allows you to just like set the different time zones. And so yeah, I threw in Beijing, Hyderabad, Boston, Seattle, where I currently am, and it's just like, okay, when can we do this? And it's never. Okay, good. So we'll see if we can make it work. But yeah, no, this would certainly not be an either or. Cool. All right, have a great evening for all of you, or a great night for all of you that are in Asia, and have a great day for everybody in the States.